Hey everyone. So this week we're doing mathematical induction. And this is a really fun topic, but also kind of a tricky topic for a lot of people. So I'm just going to work through this first example because I actually think that the first example is kind of a more clear demonstration of most of the types of problems we're going to be doing in induction. And I also don't want to make the video too long. My basic plan of attack is going to be to walk through this example, and then I'm going to talk a little bit at the end about maybe like how to conceptually think about induction, and hopefully it'll be helpful because I'm not sure exactly what I'm going to say. So this first problem says, prove by induction that for each n in the set of natural numbers greater than or equal to 1. So this is describing basically all the positive integers, or all the natural numbers aside from 0, that n cubed plus 2n is divisible by 3. So if we take any n and we plug it into this formula, if we take like the number 5, for example, and we plug it into this formula, we should see that it's divisible by 3. And we should see that that's true for any number that's greater than or equal to 1. Okay, cool. So the way we do induction, the way we do a proof by induction is through 4 steps. The first step is we're going to look for this base case, this first position where we could show that this is true, that the statement is true. And we see that the set that we're dealing with, again, is all the natural numbers greater than or equal to 1, which means the lowest number, or the base case that we're looking at, is when n is actually equal to 1. That's our base. So if we start writing out our proof, and the way you write out a mathematical induction proof is kind of this step-by-step. It's not quite similar to how we prove other things. It follows a very set kind of formula. So we have our base case, and actually, before we do that, I just want to define something real quick. And we want to use this kind of function, p of n. And so this is just going to help our notation a lot. So instead of saying this whole long statement, we're going to say p of n, or we could say let p of n be the statement. That n cubed plus 2n is divisible by 3. So, okay, now we could jump into our base case. And our base case is when we plug in 1 for the number n. So we could see how now, instead of saying let the base case be 1 cubed plus 2 times 1 is divisible by 3, we could just say p of 1, we could call it p of 1, and we could write a little extra. I like to be very wordy in my proof by induction because it just makes it easier for me to remember what I'm doing and what I'm talking about. So p of 1 is the statement that, now we're just going to plug in 1 for n. So it's going to be 1 cubed plus 2 times 1 is divisible by 3. So 1 plus, or we could even just simplify it. We could say, we could all see that 1 cubed plus 2 times 1 is equal to 3. So 3 is divisible by 3, which is true. Exclamation mark, because we're excited. We've done the base case. We've shown that this statement is true for the lowest number in our set. Our set, again, is natural numbers greater than or equal to 1. We've now shown that this statement of n cubed plus 2n being divisible by 3 is true when we plug in that first number. So that's good. So if you had no idea what induction was, you might think that in order to prove this, you might have to go number by number and now we have to plug in 2 and make sure it's true for 2, and plug in 3, make sure it's true for 3. Or sometimes we just see that n cubed plus 2n is of a form that's always divisible by 3. Like if we had, like we know that 3x, when x is a natural number, is always divisible by 3. So that's another way that you could prove something is always true. But here we don't really have either of those things. N cubed plus 2n is not obviously divisible by 3. We can't factor out a 3. And we don't really want to go through infinite examples and make sure that every single time it's divisible by 3. So that's why we have induction. That's going to give us this rule that's going to show how it's true. So the next step, which we'll do in green, is called the inductive hypothesis. And the inductive hypothesis is sort of formulaic hypothesis. It's almost a formality. I think you see in Professor Carbone's proofs, she occasionally doesn't even include the inductive hypothesis, or she rolls it into the inductive step. The inductive hypothesis, and you'll see the conclusion at the end, are sort of like very simple to write. So the inductive hypothesis says, assume that P of n is true for some n and n greater than or equal to 1. So this is just kind of a general statement of what we're trying to prove. And where I guess the key to the inductive hypothesis is that we're saying for some, that it's kind of arbitrary. It doesn't matter which n we choose. This is going to be true for some n. And yeah, okay. I wouldn't burden yourself too much on the inductive hypothesis. I think it's basically always going to follow this formula, and the only thing that's going to change is the set. Like in this example, we're concerned with the set of natural numbers greater than or equal to 1. So here, that's kind of how we're finishing our statement. Now we'll switch to pink, and we will do the fun step, the inductive step. This is when we get to do math. The inductive step is the key to mathematical induction. And basically, the inductive step says P of n implies P of n plus 1. So it basically means that we can always go a step further than where we are now. If we can show that P of 1 is true, that will imply that P of 2 is true. And if we could show that P of 2 is true, that implies that P of 3 is true. And you can see how this becomes like an infinite sequence. That's what we're going for in induction. So the way I like to write this is I want to remind myself and my reader, when I'm writing proofs, it's good to be conscious of the person who's reading your proof or grading your proof. Make it easy to understand. So I want to remind everyone what P of n and P of n plus 1 are saying exactly. So P of n states that n cubed plus, it was 2n, right? Yeah, plus 2n is divisible by 3. And okay, I'm going to do this as if this were my first time doing induction. There's something that I want to do right now, but I'll do it in a minute. And P of n plus 1 states that n plus 1 cubed, I'm just subbing in n plus 1 for n, plus 2 times n plus 1 is divisible by 3. Oopsies. Ugh. All right, so now let's do just a little bit of multiplication, and I looked at this earlier, so I know that I memorized the fact that n plus 1 cubed is equal to, that is n cubed. It would be really embarrassing if I get this wrong now. 3n squared plus 5n plus 3 plus 2n plus 2, that's this part over here, is divisible by 3. So now what I want to do, basically, here's what I'm saying. I'm saying that the fact that this is divisible by 3 actually directly implies that this is divisible by 3. That it's almost like they're mathematically equivalent statements. I could go directly from this first statement, P of n, right here, and derive this statement. That's what I want to do. So I want to start with this first statement and somehow do some algebraic tricks so that I come out with this. That's the goal of the inductive step. That's really important to understand, because that, honestly, when I was a student in this class, that took me a while to understand. I understood that P of n had to be true and P of n plus 1 had to be true, but the key is that you derive P of n plus 1 from P of n. So that's what we're going to do here. And I'll switch to white since that's what I started doing. So again, we want to restart with this P of n statement, that n cubed plus 2n. And I'm doing this slowly and methodically because I think this is really tricky. So I really want you guys to hopefully get a grasp of this. Is divisible by 3. And we're going to rewrite this so that it's more conducive to algebra. In just a second. Is divisible by 3. That is, or that's equivalent to 2n cubed plus 2n equals 3a for some natural number a, some a in the natural numbers. I could make a little comma. Okay, so this is saying the same thing. Saying that n cubed plus 2n is divisible by 3 is also saying that 3 times some number is equal to that. And another way of thinking about it is you could say that n cubed plus 2n divided by 3 equals a, and then I'm multiplying by 3. So that's how I got what I got. Now let's see if this works. Nice. Alrighty. So now my goal is to derive P of n plus 1. I have stated P of n, and I have assumed, because of the inductive hypothesis, that P of n is true. That is what allows me to start from this point. That's what the inductive hypothesis is doing here. It's saying, we're going to let you assume P of n is true. Now, just show us how you get to P of n plus 1 from there. Okay. So we want to get from this statement n cubed plus 2n, which is our P of n, to n cubed plus 3n squared plus 5n plus 3 plus 2n plus 2, which simplifies, I believe. Did I do this right? N cubed. Oh, you know, one second. Opening my computer real quick to make sure. N cubed plus 3n squared plus 5n plus 3. Yeah. Wait a second. I might have done some incorrect math here. I'm just gonna do some math real quick. N plus 1 times n squared plus 2n plus 1 n cubed plus 3n plus 1. Oh, so I did actually make a mistake up here. This 2n plus 2 is already calculated in here. So sorry about that. Hopefully some of you guys caught my mistake before I did. Okay, so we're almost there. So we want to get from this statement to this. So what do we have to do? We want to add to both sides. And we have to add 3n squared plus 3n plus 3 to both sides. Do you see how that's what's missing? That's what's in P of n plus 1. That's not in our P of n. So we're going to add that to both sides so that we could get to our statement of P of n plus 1. So that gives us n cubed plus 3n squared plus 5n plus 3, which is what we have over here, equals 3a plus 3n squared plus 3n plus 3. And now we could see that this equals 3 times a plus n squared plus n plus 1, which means that 3 divides, we'll call this the right-hand side of the equation. And here, since 3 divides this side, 3 must divide this side. That's how equations work. So 3 must divide the left-hand side, which, oh my gosh, it turns out is p of n plus 1. That is our statement p of n plus 1, that 3 divides this. So we have just derived p of n plus 1 directly from p of n. That must feel very rewarding, especially after I made that mistake and we figured out how to fix it. Yeah, okay, that's good. So conclusion. The conclusion, again, kind of like the inductive hypothesis, is a bit formulaic, but basically you just say by the PMI, which is principle of mathematical induction, P of n is true, and you have to say for the set, for what set we're talking about, for all n in n greater than or equal to 1. And if you want to be a little extra, you could say meaning n cubed plus 2n is divisible by 3. You could re-explain what p of n means, which we translated up at the top. P of n is the statement, n cubed plus 2n is divisible by 3. So you could restate that, and that's really nice form, and that will help your reader remember what you're talking about. Meaning n cubed plus 2n is divisible by 3 for all n in n greater than or equal to 1. Cool. Okay, now let's talk big picture real quick, and I'll zoom out to represent the big picture. So why does this work? The inductive step is the key. The fact that we could go from p of n to p of n plus 1 consistently, that's what induction is all about. And the inductive hypothesis allows us to assume that p of n is true. But why do we get to assume that? It doesn't seem like, it seems like we're building off this axiom that we don't actually prove. And so that takes us one step further back to the base case. So the fact that the base case is true means that p of n is true for some n, because it's true for p of 1. That's why we have to demonstrate that the base case is true. That's why it flows in this exact order. We're showing that it's true for one case. Then we're saying there must exist a case. We could assume that there exists a case where it's true. That's the inductive hypothesis, because we've already shown that it works for one case. And now we could generalize. We could say, if it works for this one case, then it must work for the subsequent case, for the next case after that. And yeah, and you could kind of understand maybe that p of 1 will be able to imply p of 2, and then p of 2 will imply p of 3, and so on until we get the entire infinite set of natural numbers, which, you know, sequentially it's not possible to reach, but conceptually, hopefully you understand how this works now. All right, so I'll see you guys Thursday. Cool.